True.
Okay, so yesterday we looked at those basics, that idea of a count and a name, and how it interacts with our numbers and our basic operations. Today, let's take a look at how that extends to the numbers we work with every day. And what helps that interaction is another basic concept, kind of like the idea of a number, that is very simple, but also very overlooked, and that is the concept of place value. We all know the place values. Starting at the decimal point, we're going backward. What's this last place value here?
Ones.
The ones. Then we have
Tens.
the tens, and then
Hundreds.
hundreds. And those are our only three place values. They repeat over and over again. Ones, tens, hundreds. Ones, tens, hundreds. Now those first three here are just our base group. The next group, of course, is the thousands. And then the billions. And most of us will never really encounter anything too much larger than that in our lives. When we name a place value, of course, we name its place value and its group. So this would just be called the tens. This is, of course, the 10,000s. I'm not going to insult you by going through how to pronounce numbers and stuff like that. There are a couple of reasons why place values are important to us. One of them is, let's say I ask you to round 1,764 to the nearest 100. You need to be able to identify what is the hundreds digit there. Or what digit in that number is the hundreds digit? 7. Now, when we're asked to round to the nearest 100, we all know how to do it. But what it's really asking us to do is to imagine you have a number line labeled only in hundreds. 3,600, 3,700, 3,800, 3,900, and hang on there. And if we put 3,764 on that number line, physically, which of those hundreds would it be closest to? To the 3,800. But we don't want to have to draw out a number line every time we round, so we were taught a shortcut. We were taught you find that hundreds place. That tells us that the sevens and the hundreds place, that tells us between 3,700 and 3,800. And to figure out which one it's closer to, you just look at the next digit. 6. That next digit, of course, is a 1, 2, 3, or 4. It's closer to the smaller one, 3,700. If it's a 6, 7, 8, or 9, it's obviously closer to the larger one, the 3,800. So since that's a 6, it tells us it's closer to the 3,800. What if that were 3,752, rounded to the nearest hundred still? That's a 7, but the next digit's a 5. 5 is right in the middle, so what do we do with that? Well, there's a couple of different ways to handle it. Most of us have been taught that next digit's a 5, you always round up. So it's going to be 3,800. There's actually a reason why. If you asked your teacher, why do we always round up, they probably told you it's just a convention. We've accepted that that's what we're going to do. That's only partially true. The truth is, this isn't just 3,750, it's 3,752. The middle is 50. 52 puts it slightly past halfway. Now you said look at the ones digit. Yeah, it's true. The only way that it would be exactly in the middle is if that ones digit was 0. It was 3,750. Then it's exactly in the middle. So we round up with that next digit to 5 just because most of the time there's other numbers after it, means it is closer to the bigger one. Even if it is 3,750, we normally would round it up to 100. There's only a couple of numbers that are really affected by that. Now, Anytime we round numbers in this class, that's what we're going to do. If that next digit's a 5, we're going to round it up. But there, if you get into mechanical engineering and mechanical design, there are some cases where if that next digit's a 5 and it's all zeros after it, well, they'll round some of them up and some of them down. So be aware of that. If you look at blueprints or whatever, and you see some dimensions that are rounded down when that digit's a 5, they didn't round wrong. They're using a different process for rounding. I'm not going to show you that process because I don't want to confuse you, but it's...
Why don't I become one of those?
Oh, come on, it's kind of fun. I was a structural construction engineer. So, by the way, since we drew out the number line, I'll show you something here. You remember these old problems where they asked you to fill in the blank? Less than, greater than, or equal to? Remember those?
You know, I think I know what you're going to do here. I just learned this like the other day.
What it's asking you is what side is the 6 on? Well, compared to the 8, the 6 is on this side of the number line. It's the arrow, the less than symbol is just the arrowhead on that end of the number line. Is that what you saw?
Yeah.
Yeah.
I was speechless.
It's really kind of cool to see that there's a reason here. It always amazed me. I never really understood math until I started. I mean, I was very good at math. Never really understood it until I started teaching.
You do it because you get by.
All those things that we were told, oh, that's just the way it is, and then you realize there's actually a good reason for it. It's really kind of weird. And well, it makes so much more sense now that you see a reason for it. We were always taught, of course, the alligator wants to eat the bigger number. So
yeah, I never understood that. What are you trying to do here?
The real reason why place values are important to us is when we look at a number like
my whole life.
263. That's the way we're used to seeing a number written. That's actually not the full number. That's an abbreviation of the number. The full number is 2 hundreds and 6 tens and 3 ones. That is the full form of that number. Now, some of us have been taught that that's called expanded form, meaning it's something unusual or special. It's not. That is actually the way that the full form of that number, that's what that number should be written. We abbreviate it 263. If I want to add that to something, let's say I'm going to add that to 522. We'll write that out in its full form. That's 500s. And 2 ones. Now, when we write our numbers out this way, it becomes obvious that each digit is a count and a name. This is not just a 6, it's 6 tens. So remember from yesterday, we talked about when we add or subtract, we have to have the same name. So that means these 6 tens can only be combined with the other tens. And these ones can only be combined with the other ones, and the hundreds with the other hundreds. That's why it was always preached to us when you add or subtract numbers, you got to line up the columns. Well, that's because we can only combine digits that have the same name. We're making sure they're lined up, so we combine digits that are the same place value. So now, when we go to add this, we've got the columns lined up, we've got the place values lined up, we just go ahead and add. 2 plus 5 is 7 hundreds. Same name. 6 plus 2 tens is 8 tens. And 3 ones plus 2 ones is 5 ones. So that is 785. Now you may have noticed I did something a little unusual there when I added. What did I do that's different from what we usually do? Started on the left side, now went to the right. Typically, when we add numbers, we start on the right side and work our way to the left. In case we have to
Add up.
there you go, carry over. You got her. You have something like 378 plus 259. I won't write this out in expanded form. I'll just do it shortcut. We're used to starting on the right and working our way back to the left because we run into this. 8 plus 9 is 17. Well, we can't have two digits in one place value, so we keep the 7 and we carry the 1. 1 and 7 is 8 plus 5 is 13. So again, we're going to keep the 3 and carry 1. 1, 3, and 2 makes 6. Well, believe it or not, this process here of carrying is a relatively new process. Now, in math, when we say relatively new, we mean in the last couple hundred years, right? But before that process was developed, the most common way to add numbers would have looked like this. 3 plus 2 is 5. 7 plus 5 is 12, so that's 2, drop the 1. 8 plus 9 is 17, so 7, drop the 1. 5 and 1 is 6, 2 and 1 is 3, and 7. We get the same answer. That's a little bit longer, but it works. Now, I'm not showing you this to change the way you add numbers. The main reason I'm showing you this is we've always been taught that in math there's only one right way to do things. That's not true. There's only one right answer, but there's several correct processes that can get you that answer. If I really wanted to, I could show you a couple more ways to add numbers. It would always give you the correct answer. I'm not going to do it because I don't want to confuse you. But that's just my point, is that there's more than one way to do things. If you have a different way of doing things than what I do, that doesn't necessarily mean you're wrong. It just means you have a different approach to it. Now, realistically, I know that you have the calculators. Probably going to use them. So before you add something like this, I would hope you would look at this and say, well, that is about 400. That's about 300. I'm expecting an answer coming out close to 700. 637 is in the right ballpark. The reason I say that is, it happens to me all the time. I've got these fat fingers. I might do 378 plus 259. You get, 296. What went wrong? The 8 didn't register. Or I might have 378 plus 9. Ooh, 2947. What happened? Extra key, right? Happens a lot. I'm not saying doing this estimate will catch every mistake, but it'll catch those big ones like that. Subtraction, as we said, follows the same rules as addition. Now, I'm not going to write them out in expanded form because I think you get the point that we can only subtract digits that have the same place value. So we have to line up the digits. So here we'll go to subtract. We've got them lined up, 1s and 10s and 100s. 7 minus 3 is 4. 4 minus 2 is 2. And 9 minus. Once again, I did something strange. I went left to right. We're used to going right to left when we subtract in case we have to round down. Not round down, but it's called borrowing, right? So we might have something like 826 minus 387. Normally, we start on the right and work our way back to the left. 6 minus 7 can't be done. Borrow from the 2, that's a 1. Comes a 16. 16 minus 7 is 9. 1 minus 8 can't be done. So we borrow from this 8 to make it a 7. This is now 11. 11 minus 8 is 3. And 7 minus 3 is 4. 439. Now, once again, borrowing is a relatively new process. One of the other potential ways this would have been done would have looked like this. 8 minus 3 is 5. 2 minus 8 can't be done, so I'm going to borrow from the 5, that'll become a 4. The 12. 12 minus 8 is 4. 6 minus 7 can't be done. I borrow from the 4, that's a 3. This is the 6. Minus 7 is a 9. So I get the same answer. That one doesn't even really take that much more time to do. Key is, again, there's multiple ways to do it. And my big point here is I hope that when you look at this, you say, well, that's about 800. That's about 400. I subtract, I'm expecting something. Multiplication. I have something like 32 times 23. I am going to write these out in their long form, full form. 3 10s, 2 10s, and 3 1s. When we multiply, we do not need the same name. So that means that these 3 10s here can not only be combined with these 2 10s, they can also be combined with the 3 1s. In fact, every digit in one number can be combined with every digit in the other number. That's all long multiplication is. It's an organized way of making sure every digit in one number gets combined with every digit in the other number. There are different forms of it, and all it really does is it changes which number we start with and what order we go through them. In this region, we typically start with the bottom number and the last digit of that bottom number. And we start combining that with the top number, starting with the last digit of the top number. So we do 3 1s times 2 1s. Now remember, when we multiply, we combine counts, but we also combine names. 3 times 2 is 6. 1s times 1s, 1 squared is still just 1, right? So it's just 1s. Then we move over to the next digit of the top number. 3 1s times our 3 10s. What's 3 times 3? 9. 1s times 10s? 10s. Anything times 1 is just a cell. Once we have combined that digit with every digit in the top number, we move over to the next digit in the bottom number. What were we taught to do down here when we did that? To leave a blank or put in a 0, depending on what process you were taught, right? The reason for that will be apparent in this next step. Well, now we have 2 10s times 2 1s. What's 2 times 2?
4.
4 10s times 1s?
10s.
10s. Putting that 0 or that space in there is just making sure we line up the place values to keep the same names. 2 10s times 3 10s? Well, what's 2 times 3? 6. And 10s times 10s? Hundreds. And now we've got them lined up because we did things correctly, so we just add. This is 6 1s, 13 10s, we carry the 1, 736. So that's all long multiplication is just an organized process to make sure every digit in each number gets combined with every digit in the other number. Again, I realize you have the calculators, you're going to use them. I would hope you'd look at this and say that's close to 30, this is close to 20. 30 times 20 is going to be about 600. So the calculator spits out 736. It's a little high, but you realize both of these numbers were rounded down. So it's in the ballpark. We're making the really bad, the really silly mistake. Now up here, we did the combinations, but we never really looked at combining, what it means to combine the counts. If I have 5 times 3. If you look back to like first grade, when you first started learning how to multiply, before you memorize your multiplication tables and you 5 times 3 was 15. How did you figure out what it was?
Count plus 5 plus 5.
There you go. Either counted up by 5s or you took 3 5s and added them together. Gives you 15. Multiplication is just repeated addition. 5 times 3 is just 3 5s added together. Well, we said that multiplication and division followed the same rules. So if multiplication is repeated addition, is division repeated subtraction? 24 divided by 6. If I take 24 and I subtract 6, I've got 18. I subtracted it once. Subtract 6 again, I have 12. That's twice. Subtract 6 again, I have 6. I've subtracted it 3 times. I subtract 6 again, that's 0. I subtracted it 4 times to get to 0. 24 divided by 6 is 4 because subtract 6 4 times. This is even where our remainders come from. Now, if we have something like 37 divided by 9. Well, we have 37 minus 9, that's 28, that's once. Minus 9, that's 19, that's twice. Minus 9 is 10, that's 3 times, and minus 9 is 1, that's 4 times. 37 divided by 9 is 4, the remainder of 1. We can subtract 9 from 37 4 times, and there's 1 left over. that make sense?
So you're just blowing our mind.
You just,
When you look at long division now, the process of long division is there to help speed up that subtraction. Let's say I have 74 divided by 2. I don't really want to start subtracting 2 from 74. That's going to take a while. Here's what I'm going to do. Rather than subtracting 2 individually, I can subtract 2 in a large group. How big of a group? Let's try 10 of them. 10 times 2 is 20. Can I subtract that from 74?
Yeah.
Sure can. How many times? 3 times. That would be 60, right? Well, that 3 times, really, I subtracted a bunch of 10, and I did it 3 times. That's really 32s. 30 of those 2s that I've just subtracted. Subtract, I have 14 left. Now I can subtract 2 from the 14 7 more times. 74 divided by 2, of course, is 37. Rather than subtracting the number individually, long division allows us to subtract it in a big bundle. Rather than subtracting 2 by itself, I subtracted that group of 10 2s. I did it 3 times, so I subtracted it 30 times there. So if I have something like, oh, let's just put something up here, 68,394 divided by 21. Again, I'm not about to start subtracting 21 from 68,000, but let's look at subtracting a group of them. How do I know how big of a group? Well, I look at the place values of the number I'm dividing. By the way, this is actually the full process of long division that I'm showing. What you were taught comes from this process, but it's an abbreviation of this process. I look at the number I'm dividing. Its largest place value is, yep, and that is in the 10,000s place, right? 10,000 times 21 is 210,000. Can I subtract that from there? I cannot. No. If I go to the next smaller place value, 1,000. 1,000 times 21 is 21,000. Can I subtract that from there? Yes. Can I do it more than once?
Yes.
Yes. How many times?
3.
Times 3, that's 63,000. So I subtracted a bundle of 1,021s. I did it 3 times. 1,000 times 3 is 1,000. That 63,000 that I subtracted is really 3,021s. Subtract here, I get 5,394 left. My next place value is the 100s place. What's 100 times 21? 1,100. Can I subtract that from what's left?
Yes.
Yes, more than once. Times 2, very good. 4,200. I subtract, I've got 1,194. What I just did there was I subtracted a bundle of 121s, and I did it twice. 100 times 2, subtracted 221s. Next place value is 10. It's 10 times 21, 210. Can I subtract that from what's left?
Yes.
Yes. How many times? 5 times 210 is 1,050. So subtract, I've got 144. So what I did there is I subtracted a bundle of 10 21s, and I did it 5 times. 10 times 5 is 50. So that 1,050 was really 50 of those 21s that I subtracted. Last place value is 1s. 1 times 21, of course, is 21. I can subtract that. It won't quite go 7 times, will it? It's going to be times 6, it'll be 126. It'll be 18. That was, of course, 1 times 6, or 6 more of them. That gives me 3,256. Remainder Now you might be looking at that saying, that looks nothing like what we were taught to do on division. Actually exactly the same process, just we were taught was severely shortened. We were taught to do this. Look at this. 21 go into 6. No, so you leave it blank above the 6. As we tested this, it was too big. We moved to the next place value. Move over to the 8. Does 21 go into 68? Yep, 3 times. 3 times 21 is 63. Track to get 5. But what we did there was exactly what we did here. We just left off all those zeros. Now, depending on who taught you the process, some of you just bring down the next digit, some bring down the rest of the number. Either way, we're only moving over to the next digit. 21 goes into 53 twice. 2 times 21 is 42. 11 times. Again, same process. Just left off all the zeros. Make sense?
Am I even eating right? I don't even know.
Yeah. Well, listen, I'm not trying to change the way you divide. I just want you to understand where the process comes from. To be honest, when I really started learning about math theory, when I started teaching, I became very angry at the math I had seen when I was younger because why the heck didn't somebody teach me? And then I realized just nobody had taught them. A lot of this has been lost for several generations. We've tried to make it easier for people to do math, so we've shortened it, made it simpler and simpler and simpler until we've lost the whole effect of what's really going on. So hopefully seeing how it's done makes it a little easier to remember the process. Rather than just memorizing this process, you know where it comes from so you can remember it a little easier. Now with that said, again, I'm hoping you'll look at this and say, oh, that's about 68,000 divided by about 20. 68 divided by 2 is 34. Cancel out a 0, that's about 3,400. So when you get 32,500 or 3,256 with some left over, you feel like that's okay. What would that be now? 3,256 point. Divided that out as decimal. Okay. One thing you learn, there's 2 things about math that really enlighten you. One is to see that there's actually, once you see the count and the name and the 2 parts of the numbers, and you see how all the operations work with those parts, that there's really only like 3 processes. Once you know those processes, everything else kind of falls into place. The other is that the calculations in math are all about patterns. One of them is dividing by 7, which is really all that was. 18 over 21 is really 6 over 7. Give me a random number between 10 and 40. 36. Wow.
You get out of here.
36 divided by 7 is 5.142857143. How do I do that? Well,
You just do.
there's a pattern dividing by 7. 7 goes into 36 5 times. That's the 5. There's 1 left over. A 1/7 is 0.142857 repeating. Let's say it was 37 divided by 7. That would be 5.2857142. Again, how do I know that? Well, that's just 5 2/7. 2/7 is 0.28571. Notice anything familiar about those numbers? Same numbers, right?
7.
Yeah, same numbers, same order, just starting in a different spot. 7ths. 0.428571. Again, same numbers, just starting in a different spot. These patterns occur all over in math. Dividing by 13 is a similar pattern. Decimals.
9 has a one, cool one too.
9 has the, yeah, that's a little bit simple. It's only a 1-digit pattern instead of multiple.
I like the 9s.
As a general rule, by the way, when you're dividing by 7 has a 6-digit repeating pattern. If you divide by a number, if it doesn't come out to be an exact number, if it's a repeating decimal, the pattern, the repeating pattern will never be more than 1 less than the number you're dividing by. So 1 less than 7 is 6, so that repeating pattern will never be more than 6 digits. 13, if you do 1 divided by 13, that pattern will never be more than 12 digits long. Now, I don't think this calculator will give me 12 digits. It does. 1 divided by 13 actually repeats in 6 digits. But some of the others, I think 3 divided by 13. It does. So it'll never take more than 1 less than that number to get it to repeat. I do a lot of calculations in my head, not because I can calculate that quick, and it's not because I have them memorized, because there are a lot of patterns in math. So your first homework assignment for the course, in your book, page 8 to 10, 1 through 69, the odds. Now remember, I mentioned yesterday that homework is not collected and graded. The homework is a tool for you to learn, especially in these first couple of weeks. I don't want it to come across as I'm telling you not to do the homework, because that's not what I'm saying. But do the first problem or two, and if they seem really easy, feel free to skip ahead a few to some of the more difficult ones. Do enough so that you are very sure that when we do a quiz, possibly on Thursday, that you're ready for it, and you're comfortable with the material. Also, I was going to check here. I don't know if I have it up here. So our first quiz is on Thursday. Our first test is next week, Thursday. Just so you're aware of that. There will be a second quiz probably like Tuesday or Wednesday of next week. Okay, well, that. Usually I give you the last 10 minutes or so to work on homework, so I want to get